Tests for Convergence, Part 4. The Alternating Series Test. I believe this actually will be our last test for convergence in this fourth video. When the terms of a series alternate signs, positive, negative, we call the series an alternating series. It could appear like this: sigma -1 raised to the nth power times a sub n, or it could look like this: sigma -1 to the n minus 1 times a sub n, and both of these are n starting somewhere, usually 1, and going to infinity. There's other ways it could appear. It'll have -1 with an exponent involving n, -1 with an exponent involving n, with a sub n next to it, where a sub n will always be positive, and -1 to the n will alternate signs. It'll change back and forth. An alternating series converges if a sub n is greater than or equal to a sub n plus 1. And by a sub n, we mean just this part of the nth term, not counting the -1 with the exponent. And the limit of a sub n, that's just what has the green box around it, over here, or over here. The limit of that, as n approaches infinity, is equal to 0. If we can demonstrate that both of these are true, we can say the alternating series converges. So for example, the alternating harmonic series, the following series is called the alternating harmonic series. It looks like this: sigma -1 raised to the n plus 1. Notice -1 with an exponent involving n, over n, and going from 1 to infinity. It also could look like this: sigma n equals 1 to infinity, -1 raised to the n plus 1, with 1 over n next to it. Recognize the harmonic part there. Replacing n with 1, since 1 plus 1 is 2, -1 squared is positive 1, with positive 1 times 1 over 1. But when n is 2, 2 plus 1 is 3. -1 to the third power is -1. So we have -1 times 1 over 2. When n is 3, 3 plus 1 is 4. -1 to the fourth power is positive 1. So we see the signs alternating: positive term, positive, negative, positive, etc. And so this is the alternating harmonic series because the signs alternate. So note the obvious that any of these counting numbers, 1, 2, 3, etc., will be less than that number plus 1. 1 is less than 1 plus 1, 2 is less than 2 plus 1, etc. That's obvious. When we take the reciprocal of both sides, less changes to greater. In this particular example, that right there just happens to be A sub n. Because in this test, the alternating series test, when we say A sub n, we're talking about just this. Ignore the -1 that makes the signs alternate. Ignore the alternator. And in this particular example, that right there is A sub n plus 1. Because it's A sub n with n plus 1 in place of n. So bring this down because this is that and this is that. So I'm going to check off the first condition for convergence. For an alternating series to converge, we need that to be true. We just showed that it is. We also need the limit of the nth term as n approaches infinity. When I say the nth term, though, in this test, I'm just talking about what has the blue circle around it, disregarding the sign alternator. The limit, in this case, of A sub n as n approaches infinity is 0. So check off the second condition. In the alternating series test, there's only two conditions. A sub n has to be greater than A sub n plus 1, and the limit of A sub n as n approaches infinity has to be 0. Both of those are true for this series, the alternating harmonic series, which proves the alternating harmonic series converges. Sigma -1 to the n plus 1 over n, which is called the alternating harmonic series, actually converges. Even though the harmonic series, where the signs do not alternate, that series, the harmonic series, the regular harmonic series, diverges. So here's some vocabulary, important vocabulary. The alternating harmonic series converges. We proved that using the alternating series test. But since the regular harmonic series, which is this series but with all positive terms, diverges, we say the alternating harmonic series, the one that has the -1 to the n plus 1 over n, we say that alternating series does not converge absolutely. We say that it converges, but it does not converge absolutely. And that just means when we take the absolute values of all the terms, we get a series that does not converge. When a series does not converge absolutely, but it does converge. We say that it converges conditionally. The alternating harmonic series does not converge absolutely, absolute value, but it does converge. We're going to say it converges conditionally. So think of it as converging under the condition that you keep the signs alternating. Another example of the alternating series test. Sigma, -1 to the nth power, times n squared over n squared plus 9. N starting somewhere, 1 going to infinity. So this is the alternator. It makes the signs of the terms alternate back and forth. And this is what's referred to as A sub n, just with the red box around it, in the test. There's two conditions. But here we right away note the second condition in this test is the limit of A sub n as n approaches infinity. In this case, it's the limit of what has the red box around it. Which is the limit of 1 over 1 plus 9 over n squared, which is 1. And that's not 0. So of the two conditions for the alternating series test, the second condition is not satisfied. So this alternating series diverges. The alternating series in this example diverges. One more example. Sigma, sine n pi over 3 over n squared, n going from 1 to infinity. The reason this is alternating is because when we make n 1, then 2, then 3, and so on, this changes from positive to negative to positive to negative. So think about some trigonometry. The sine of 1 pi over 3 is a positive number. When n is 2, the sine of 2 pi over 3 will be a negative number, and so on. So the signs will alternate. And there's two conditions for the alternating series test, which this is an example of. The second condition, where the limit of A sub n as n approaches infinity, has to be 0. In this case, it is because the nth term when we say the nth term, we mean disregarding the positive or negative. So here's some thinking needed here. Even though this is alternating positive, negative, it's never ever, well, let me say it this way. This thing I just circled is always between -1 and 1. The sine of an angle is never more than 1 or less than -1, no matter what. That's a fact about sine. So if we have a number up here that's always fluctuating somewhere between -1 and 1, and we're dividing by infinity squared, any number no more than 1 divided by a huge number, that will be 0. So there's your second condition for the alternating series test. The limit of the nth term as n approaches infinity is 0. Like it's supposed to be. Also, the sine of n pi over 3 over n squared. Absolute value of that is always going to be less than or at most equal to 1 over n squared for the same thing I was just talking about. This numerator is always, it's a sign of something, so it's always between -1 and 1. That means this has to always be less than that. This numerator, the absolute value of this, the most it could be is 1. It can't possibly be greater than this. And this is the nth term of a p-series that converges. In the blue box there, that's the nth term of a p-series that converges. Because a p-series, 1 over n to the p, converges when p is greater than 1. P is the power. So by the comparison test, we have the nth term of the series, this series, being less than the nth term of a series that converges, less than a series that converges, so converges. So we're going to say sigma sine n pi over 3 over n squared. Converges absolutely, because we're looking at the absolute values of the terms. The terms are actually changing sign, but the absolute values of them will always be positive. And when the series with all the signs positive converges, we say the series converges absolutely. Absolutely. And anytime a series converges absolutely, by changing all the terms to positive, then the original series converges, period. Absolutely. The end.